Welcome to homework.
Difficult one. We got a harmonic oscillator in its first excited state, and it's n equals 1 state. We have its wave function with an unknown normalization constant, and this parameter a equal to m omega over h bar. We're first asked to plug this wave function solution into the time-independent Schrodinger equation, and to confirm that it is in fact a solution. We're then asked to find the normalization constant A1 by normalizing the wave function. And finally, we're asked to show that the probability amplitude is minimum at x equals 0 and the turning point's plus or minus 1 over a. So this is going to take a while. It's a pretty difficult problem involving a lot of differentiation and integration. So let's jump into it. So to start off, we got our time-independent Schrodinger equation. We should probably write out. Before we can write out our energy levels. E1 is going to be 1 plus 1/2 h bar omega, which leaves us with 3/2 h bar omega. Okay. And of course, we have that the potential for the harmonic oscillator is always 1/2. So at this point, we can use the time-independent Schrodinger equation in this form. Psi double x is equal to 2m over h bar squared multiplied by 1/2 kx squared minus our energy 3/2 h bar omega times the wave function psi of x. This is a perfectly reasonable way to write out the time-independent Schrodinger equation. So what we need to do now is compute some derivatives of psi. Let's write it off once again, off to the side. We have a1 x e to the negative a squared x squared over 2. So we can use the product rule and the chain rule to compute some derivatives. Our first derivative is a1 over 1 minus a squared x squared e to the negative a squared x squared over 2. And our second derivative is a little a squared x squared minus 3 times ax e to the negative a squared x squared over 2. And of course, because we're doing derivatives and integrals of exponentials, we can actually write this out in terms of the original psi. This will be kind of useful to us later. So if we take our second derivative, we can write this out as a squared x squared minus 3a, and then just multiplied by the original wave function, psi 1. Okay. So I didn't show some of the steps there, but we just took some derivatives using product rule and chain rule. I'm sure you know how to do that. So now we can plug in our second derivative of psi into the Schrodinger equation and start chugging away at it, try to simplify it down to the point where we can show that these are in fact equal to each other. Okay, so plugging in our simplified form on the left side, psi 1 x. And we can start doing some work on the right-hand side as well. Okay, we'll leave this for now. So it's immediately apparent that we can actually drop the original psi 1 out of both sides, which is very helpful to us. And we're left with 2 terms on both sides, which is good. That's what we expect. So let's move on. We have when all things are said and done, a to the 4 x squared minus 3 a squared equals 2m h bar squared 1/2 kx squared minus 3/2 h bar squared okay. So now we can start expanding in A. This might take a bit of time. So this will end up being m omega for h bar squared times x squared minus 3 m omega over h bar. And when we move this 2m over h bar squared through these two terms, we can start getting them to look a lot like the left-hand side. mk over h bar squared, x squared, minus 3 m omega over h bar. So we already have the second terms matching. We just need to reorganize this term here. We can do that by making use of the fact that omega equals root k over m. We can do that to this term on the left-hand side. Once we do it, we have m squared over h bar squared times k over m. And this is what we need. So this term is the same as the other term. mk over h bar squared, x squared. And then doing just one more step of algebra, we get our mk over h bar squared, x squared, minus 3 m omega h bar, same term. So we're good. So we have the left-hand side obviously equal to the right-hand side, and that shows that this is in fact a solution of the time-independent Schrodinger equation. Okay, so on to the next step. We need to normalize. We know that to normalize something, we need to integrate it over all its allowed space. In this, for the oscillator, we can go from infinity to negative, from negative infinity to infinity of psi squared dx. Once we do this big integral, it needs to equal 1, and that's going to allow us to set the normalization constant. So this is equivalent to saying we got our a1 squared x squared e to the negative a squared x squared. So I squared the wave function, and this is the integral to do. This is not an easy integral. This is called a Gaussian integral. They appear in a number of contexts. It's not a straightforward integral to do. We can make use of a table or any kind of software we want, or we can actually, there are some ways to brute force it. I'm going to use the result for it. We can first pull out this a squared to the other side, because it is a constant after all. And this integral will collapse down to the following. It'll collapse down to root pi over 2 a cubed. And from here, we can pretty clearly see that a squared is equal to 2a cubed, little a cubed over root pi. Thus, the normalization constant is root 2 over root pi a to the 3/2. Okay. So now on to the very last step. We have our normalization constant. We now need to find the minima in the probability amplitude. So we're trying to minimize our psi squared, our full psi squared, which with everything included comes out to be 2 little a cubed over pi, over root pi rather, times x squared e to the negative x squared, a squared x squared. So like all problems where we're trying to minimize something, we need to take a derivative of this. So d of psi x squared dx is going to need to be equal to 0. We're going to find these critical points. Once again, I'm not going to show all the steps to doing this derivative, but it can be done. It's not too bad. We are left with 2a cubed, the original constant. It's left unchanged, times 1 minus a squared x squared times 2x e to the negative a squared x squared. Now, for this to be equal to, we have a product of things. For this to be equal to 0, either this needs to be equal to 0 or this needs to be equal to 0. So let's start with this one. It's clear that for this second term, x needs to be equal to 0. This is that middle point, and this works. And specifically, if we plug x equals 0 into the original wave function, you see it's 0. So this is definitely a minimum because it's always has to be positive or 0. So this is good. If x is 0, this is definitely a minimum. So if we look at this second, so in the case that x is not 0, we look at this term right here in the parentheses. It must be true that 1 minus a squared x squared must be 0. We can solve for x, and we see that it's clearly plus or minus 1 over a. And those are the turning points you're asked to find. So that's it. Thank you very much.